Hey everyone, behind me you see the next evolution in my quantized inertia capacitor thrust experiments. I started with a precision scale, then I tried a pendulum setup, and with some success actually, but now I'm moving on to a more sensitive measurement instrument, and that is a torsion balance. So let me show you how it works. Now you may wonder what this contraption is. You see a very thin tungsten wire hanging down, 0.12 millimeters. This is my 1.44 nanofarad thrust capacitor wrapped in Kapton foil. Then there's this 3D printed balance beam. Yeah, it's a bit odd, but this allowed me to place the circuitry for generating the electricity in there as well. So it's a tiny 100 milliamp hour LiPo battery, 3.7 volts, that goes into this €6 AliExpress circuit board. It's an arc igniter board, but the cool feature is, you see it here, it's a little antenna. It's remote controlled, so that's pretty awesome. So no interference of me touching anything, or I don't even have to get near it for it to trigger. So that's great. So it transforms the 3.7 volts to over 10 kilovolts, which charges the capacitor. There's a tiny diode, high voltage diode there. It's hard to see. So there's a high voltage diode. It charges this plate positively, the other plate negatively. And then once it reaches 4 kilovolts, it discharges through this little gas discharge tube. And the idea is then that we'll see a deflection. So the cool thing about a torsion balance is that the main resistance it experiences is the twisting of the wire, which is of course very minimal. And because it's so sensitive, you see this little fin on the back, which is slightly submerged in a little bit of water. And that is a damper. So if you wouldn't have that, it would keep like oscillating forever, which means, you see I came a bit closer now, it already starts to move. This makes sure that the oscillation is damped a little bit, and it returns to its rest position faster. So that's why that's there. So let's give it a go, see if it does anything. I placed my torsion balance inside this plastic container so that airflow cannot interfere with it. And we're gonna test it out, see what happens when I fire it up. Okay, I placed my camera on a tripod. The balance is hanging completely still. And I'm gonna fire it up now and see if we can spot any movement. We expect movement in the leftward direction because that is the anode, and we expect movement towards the anode. So I'm going to press the button. And it is definitely moving in the leftward direction. Now it's swinging back. That's awesome. Fired it some more. It's definitely moving. That's great. So this can still potentially be explained by ion wind. So we're gonna have to perform the same experiment in a vacuum chamber. I've already been looking at a couple of them. They are not cheap for this size. But yeah, there's no other way. So I'm gonna have to spend a couple $1,000 to perform this experiment, but if that proves capacitor thrust as predicted by quantized inertia, then I'm willing to do that. Okay, so I was quite happy with that result. To some it might seem very underwhelming, just the tiniest deflection, but you have to realize that we're just pulsing it a little bit. So just a couple of impulses are what create this thrust. And we have a fluid damper, so it's the fin is scraping through a bucket of water behind me. The whole situation, like the whole balance beam with the circuit on top of it, the capacitor and its insulation and everything, it weighs probably around 100 grams. So it is moving all of that and then through the water as well. So it's actually quite impressive just for a couple of impulses. So yeah, I'm stoked, and I'm gonna spend some money on a vacuum chamber, and then I'll get back to you. See you later.